Alright, today I want to go through a math problem that was posted in a video by 3Blue1Brown. So this problem was left as an exercise during the video, and I put the link to the original video in the description. So I found that the answer and in general this problem was really interesting, so I thought I was going to make a video on the solution. The problem is the following. You have this sum of an infinite series. F of x is the sum from 0 to infinity of ak x power k, where ak is some arbitrary series for x between 0 and 1, and of course we assume that this sum converges. And the question is, what can you tell about the coefficients of f of x divided by 1 minus x? It's a fairly open question for math problems. So the way we're going to tackle this, since we want to find coefficients of this, first thing that comes to mind is, well, we can see coefficients for f of x. Can we find coefficients for the other part of this? So if we call h of x is equal to f of x over 1 minus x, we can say that this is f of x times g of x, where g of x is 1 over 1 minus x. And there is a very common expansion of this as a sum of an infinite series, which is the following: k equals 0 to infinity of x power k. If you are not familiar with this, there is a not very rigorous but simple way to at least get the intuition behind this formula. So if you have the sum from 1 plus x2 to infinity, and you call this, let's call this L, and you assume that it converges, which is key, assume that it converges to one number, then you can show that if you multiply this by x and you add 1, you get the same thing, right? So if I multiply by x, I get xl is equal to x plus x2 plus x3, etc. to infinity, and I add 1, so 1 plus xl is 1 plus x plus x2 plus x3, etc. And now you notice that this is exactly what we started with, right? So we can write 1 plus xl equals L. And then if you just rearrange these terms, you find that L is equal to 1 over 1 minus x. That's how you can get the intuition for why this is true, why 1 over 1 minus x is the sum of the powers of x. So using this formula, what we can do is basically write h of x is equal to, so we have the sum of the akxk, so 1 plus, sorry, not 1, a0 a0 plus a1x plus a2x2, etc. This times 1 plus x plus x2 plus ... And so we'd like to basically expand this and figure out what the coefficients that we get are. And here, maybe you can already kind of visualize what the result is going to be, because what do you get when you multiply by a polynomial like this? What you can do to get this idea is, let's just write this as f of x. So this is f of x times 1 plus x plus x2 plus ... and we can just expand this, right? So we get f of x plus x f of x plus x2 f of x. All right. Now let's put in a table form the coefficients in this formula in front of each power of x. So what would be the coefficient in front of 1, in front of x, in front of x squared, in front of x cubed for h? And we can write h as the sum of all of these terms. So the first term is f of x. F of x, the coefficient in front of 1 is a0. In front of x is a1, a2, a3, etc. Then we have x f of x. What happens when you do this? When you do x f of x, you will get, essentially you just shift the coefficients if you want, because you get x a0 plus x2 a1 plus x3 a2. So now the coefficient in front of 1 has become 0. The coefficient in front of x is a0. The coefficient in front of x2 is a1. So here we have 0, a0, a1, a2, and then x2 f of x. You see that this basically you do the same thing. You just shift again, so you get a0 here, a1, etc. And you're gonna get this kind of like a triangle. And now when you take the infinite sum of this, which is h of x, you can see that you're gonna get a0, a1 plus a0, here a2 plus a1 plus a0. And so like this we can get the intuition as to what is going to be the end result. So it seems that we're going to get essentially each coefficient is going to be the partial sum of the AKs. This is not a rigorous proof because you need to be careful when you do infinite sums like this. You cannot just rearrange terms as you want, or you can get nonsensical results. So let's just write down some notation, and we're going to just prove this. So here I'm going to write that, well, we're going to write the partial sums. So let's define fn of x as the sum from k equals 0 to n of the ak xk. We're going to define gn of x is the sum from k equals 0 to n of xk. And we're going to call hn of x is going to be fn of x times gn of x. We're going to expand this, and we're going to find the coefficients and find the result from here. We are also going to write down let's write an is equal to the sum from k equals 0 to n of the ak. Partial sum. All right. So with these notations in mind, let's write down, let's try to expand hn and see what we get. How are we going to do this? We're going to write hn of x is equal to, so the partial sum, we're going to have 1 plus, sorry, not 1, a0 plus a1x plus dot 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 plus anxn times 1 plus x plus dot 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 plus x power n. So we could do the whole thing, like the whole expansion, and compute it, but I'd like to visualize it. I'd like to show you a good way to do this kind of development without having to actually, well, you know, write equal, then look at, okay, a0 times 1 is a0, a0 times x. You can do this a little bit more systematically by just essentially doing a table like I did earlier. We're going to look at what should be the coefficient in front of 1, what should be the coefficient in front of x, in front of x squared, etc. in front of xn minus 1 and in front of xn. So when you think about it, the coefficient in front of 1, there's only one, right? It's going to be the coefficient in front of x power k is whichever terms here where the power coming from the top plus the power coming from the bottom is equal to k, right? If I want the coefficient in front of x2, it's either going to be here the term in front of x2 times the terms 1, or the terms in front of x times the term in front of x, or the terms in front of 1 times the terms in front of x2. So if you use this technique to develop it, in front of 1 you just get a0, right? In front of x, so you get whatever is the term in front of, so you get a0 here plus a1. Here this is a0 times x plus 1 times a1. In front of x2, so you're going to have a0 here times x2 here, plus a1 here in front of x, and here you get a2 times x2 in front of 1. This looks like this. Let's actually add a middle term here, which is going to be x power n, and then x power 2n. Yeah, but it goes actually all the way to 2n. A little mistake I was making, because yeah, you're gonna have x power n times x power n. So this goes all the way to xn, and you're gonna essentially here get the sum a0 plus a1 plus all the way to an. Now what happens after? So in front of n plus 1, you cannot have a0, right? Because a0 times whatever is here is never going to give you x power n plus 1, because the largest term here is xn. You're going to have a1 xn plus 1. So essentially it contracts like this, with a1 plus a2 plus dot 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 plus an, and then all the way down to an. So we have these two pyramids like this. Well, so we have this shape where it expands like this and then it contracts. Now, how can we express? So this part is easy to express algebraically. It's just the sum of the ak, which we've defined as a n. Now what about this part? So this part, you can think of it as the total sum here. So let's call this, well, this is essentially an. This is an minus a0, right? We're just missing the first term. You then have here an minus a1, which is a0 plus a1. And finally here you have an minus an minus 1, and you could even say that there is another term here which is an minus an. So if you think about it this way, you have here a0, a1, etc. is the same pyramid that we have there. So you just have an minus your original pyramid, right? a0, a0 plus a1, a0 plus an. So let's try to write this down. What we have when we develop this is hn of x is equal to the sum from k equal 0 to n of the ak of the AK, like this. So that's the sum of all of these terms times x power k, right? So this is the first term is going to be a0 times 1. The second term is going to be a0 plus a1, which is big A1 times x, etc. all the way here. So we just reached this part. Then the rest is going to be plus. We have here, we can essentially take, so this is going to be xn plus 1, which we can write as xn plus 1 times 1, all right? And then the next term is going to be xn plus 2, which is xn plus 1 times x. So essentially we can factor out this xn plus 1 and put it in front. So we have xn plus 1 times the sum from k equals 0 to n of this, well, an minus ak times x power k. Now if we rearrange this a little bit, we're gonna get here this an we can take out because it doesn't depend on k, and this ak xk is the same as this. So let's just not rush it. I'm just gonna write down the whole thing. K equals 0 to n of ak x power k plus x n plus 1 an sum k equals 0 to n of xk plus x n plus 1 sum from k equals 0 to n of ak x power k. So at this point we just group the same terms, so we see we can group these two. Let's write it down. You have 1 plus x power n plus 1 times sum k equals 0 to n of ak xk plus, and that's the term that remains, x power n plus 1 an, the sum from k equals 0 to n of xk. All right. So let's look at this formula. Let me erase this. So what we have here is a formulation of the partial sum of h, and we want to study it and check what happens when n tends to infinity. So when n tends to infinity, you're going to have this term here, which is going to tend to 0, right? This, we have to make an assumption here. We have to assume that this is this converges to something, right? Otherwise the whole thing diverges. And this tends to 0. This we have to assume that it converges to a also, and this tends to 1 over 1 minus x. So overall, this whole term will tend to 0, and this tends to the sum of the ak xk. So assuming that this sum converges, we have this formulation. And we also know that because hn of x is one partial sum of h of x, we also know that hn of x tends to h of x when n tends to infinity. So that allows us to show that h of x is equal to the sum from k equals 0 to infinity of the ak xk. And so yes, that's a I find it a very cool result. It means that when you do this division by 1 minus x of this series here, you're basically transforming this sum into a sum of sums, right? Because the AK, remember that this is the sum of the AKs. And of course, this feels fairly intuitive when you look at the table that I drew at the beginning, where you realize that this this polynomial 1 over 1 minus x, which is actually also the sum of the xk, is actually taking your original series and shifting it repeatedly and summing it all together. So yeah, I thought this is a really cool little math exercise.